All right, physics reaction video number 79. Today it looks like we're doing double slit. I don't know if it gets into multiple slits. Looks like the title seems to be just double slits. So here we go.
Okay, we're at 36.3, but before we go on, I'm going to make sure that everybody understands what these different modes are. So we're going to assume that what they're talking about here is centered, so that for the brights, we'll have the brights and the darks over here. This is m equals 0. Of course, this is m equals 1, m equals 2. This is m equals minus 1. Oh, it looks like a 2. M equals minus 1. M equals minus 2. And so if we have the plus or minus 1/2, this would be m equals 1/2, m equals 1 and 1/2.
Oh, interesting.
M
interesting that he didn't write that as 3/2.
2 and 1/2.
But
and over here, of course.
Yeah, so this is interesting. So I think my instinct would have been to do 3/2, 5/2. But I really, really like this, breaking it down so that there's an integer, which is this integer, plus a little half. It's an integer, this integer, plus a little half. I actually like that, and it's going to make this one be -1/2. It's so interesting. I actually have always hated this way of writing fractions. I almost always make it, I don't know, they have some name for it in 5th grade or whatever. I would have always written this as 5/2 and this is 3/2 because this just looks like you're multiplying 2 times a half, right? And so I've never really liked this structure, but for this particular topic, it's actually really, really useful. I never thought about that before. Very cool.
M equals minus 1/2, m equals minus 1 and 1/2, m equals minus 2 and 1/2. Just wanted to make sure that everybody understands what these modes are and what they're pointing to. Sorry if my handwriting isn't that clear, but I think you get the idea. Now let's get back to the PowerPoint, which is right here, and it's the same image. I can't write on this with I can do it on my iPad, not on.
Well, I see what he's saying from a technological perspective. He has it in one place where he can write on it, and then he's got a PowerPoint set of slides, which he very seamlessly flipped to, but he's unable to write on this. So that's really intriguing. I'd love to hear you guys' perspective on this, right? So you can have sort of an infinite whiteboard that you scribble all over, and then if you share it with your students, it seems like a bunch of mishmash because they only see the finished product. Versus something clean like this, which you could share with them, and then as you're presenting it, maybe pause and go over to, just like what he's doing, go over to something that you can draw on. So I'm intrigued by that. From my perspective, I tend not to share my slides, right? So I say, here's this video, this is your notes. So I tend not to share the PowerPoint. So I feel like they can just rewind and fast forward the video if they want, but I actually don't know how well received that is. I mean, of course, there's some vocal students who say they like it a lot, but it's not 100% clear if it's actually the right choice.
On this, so this is what the image looks like, and note that the edges of the bright fringes in the figure, they're not sharp. There's gradual change from bright to dark, and so we consider the distribution of the light intensity associated with the double slit interference pattern in this section. So the intensity is equal to the maximum intensity.
So it's interesting that then to flip it, right? So to show it as in the vertical orientation we had before, and then to flip it to the horizontal so that you can line it up with this, right? Because you could have flipped this, but then you would have had to turn your head to read all of this stuff. So I actually like that, because I think that It's helpful for the students to understand that this pattern is just oriented with the slits. So if your slits are oriented vertically, then your pattern will be oriented vertically. And if your slits are oriented horizontally, which can often happen, then you get it horizontally. We actually did this experiment we would paint glass slides with black paint and then take a razor blade and go and then just shoot lasers through it, right? And so then you're just holding this so-called double slit when you're shining it on the wall or whatever. What's not clear to me is whether this is sort of well into the lecture or if they've seen this stuff before, because this, obviously we expect some sort of sinusoidal or cosinusoidal thing. Has this all been developed already? It's not clear. Probably it has. But now we're trying to understand, okay, how can you interpret this image using this formulation?
Max times the cosine squared of pi d sine theta over lambda, where lambda is the wavelength. Now for small angles, I equals I max cosine squared theta d over lambda L times y. If you go back there, we saw the y over. I think we saw the. I think we may have seen the L over y for tangent theta, but for small angles, tangent theta and sine theta are the same. So this is the diffraction grading, and these are the for any value of n, the decrease in intensity and maxima to the left and right of the central maximum indicated by the blue dashed arcs is due to the diffraction patterns.
So what's interesting about this diagram is that right, like n equals 1 would be nice. N equals 1 is this dashed line here, right? And it's interesting that I'm thinking he must have gotten this from the book. It just looks so professional. It's interesting that it's not extending down to where this goes to 0, to what is often called the missing the missing band or the missing peak. Yeah, I mean, obviously what's being talked about here is these number of little sub-minimums, right? So the number of sub-minimums is always n equals 5 minus 2. So 5 minus 2 is 3, so there's 3 humps here. There's lots of really cool ways to motivate why that would have to grow. And of course, once you know there needs to be more of these, to sort of fit them in, you got to squeeze these so they get narrower, right? So they get these really, really sharp, bright peaks. But regardless, you always get this curve which comes about from the shape of this of each individual single slit. So I think it's really, really interesting when you look at how these books describe it. They do the double slit and all these other slits before they come back and do the single slit, because it turns out the single slit is much harder. The single slit is this weirdo integral that gets nasty, whereas these are just algebraically adding up a finite number of terms. So I've always found that to be fascinating. If you spend a ton of time on the single slit, you understand this shape. And so sometimes you have to sort of come back and say, hey, remember when we showed you that diagram, we kind of ignored this dashed line here, but now let me talk about it. So I always find that really, really interesting. I'd love to hear from you guys which way you go about doing it.
From the individual slits, which are discussed in chapter 37. So it's not part of this. So,
so the next chapter.
Primary maximum and a secondary maximum. And you can see as n increases, you get these many more secondary maximums. Here it just looks like a broad line for n equal 10, but you can see there's a lot of different secondary maximums. So
I just want to pause there for a second and talk about these maximums. What's actually easier to motivate if you use the phasor diagram, right, where you just have these phasors you're adding, right? And so if you've got two phasors, they're going to be maxed out like that, right? And they're going to be minimized. The only way to minimize two phasors is to come all the way around and have them cancel each other like that. And so there's only one way to have a minimum with phasors. So that's why there's only one minimum. If you have three phasors, there's actually a couple of ways to make three identical phasors add up to 0. It's basically a clockwise equilateral triangle and a counterclockwise equilateral triangle. Keeping in mind that with the phasors, their relative angles have to be the same. So if you have two, you can have any relative angle you want. But with the third one, the next one has to have the same relative angle because they're evenly spaced. So it turns out with 4 phasors, there's 1, 2, 3 ways that you can make them add up to 0. This is a clockwise circle. This is there and back, there and back. This is a counterclockwise circle, right? And so what I do is I motivate the number of minimums, which then helps you understand how many maximums there are. Just reading this, using the figure for 6 slits. Oh, very, very cool, right? So, okay, I've shown you a pattern. Can you guess what's going to happen at n equals 6? That's super cool.
Yeah, let's see. I think that's all there is to discuss about this. Now, using the figure as a model, sketch the interference pattern from 6 slits. Well, they jump from 5 to 10, so it's going to look a little bit like 5, a little bit greater. There's going to be more of these bumps here. So we've seen 1 bump, 2 bumps, 3 bumps. So there's going to be 4 bumps for the n equal 6, and sure enough, you can see 1, 2, 3, 4.
Cool.
This is what the 6 slits.
So using the phasor analysis, the middle one is there and back, there and back, there and back. This, I believe, is a hexagon, a clockwise hexagon. This minimum is a counterclockwise hexagon. This is a clockwise triangle that goes around twice. This is a counterclockwise triangle that goes around twice. And this is there and back, there and back, there and back. That's the only 1, 2, 3, 4, 5 ways. 1, 2, 3, 4, 5 ways that you can get 6 phasors with a fixed relative angle to add up to 0. That's super cool. I really like how this question was the perfect question to ask after this diagram, and then to be able to go, bam, here it is so useful after getting students to think about it.
Look like, and that's the end of the 36.3. It's just the intensity, we won't. I don't even think I assigned a homework problem with this, but here it is. The I equals I max cosine squared of pi d sine theta over lambda, or for very small angles, pi d over lambda L times y. Okay.
So very cool. It's interesting, right? He said he wasn't sure if he assigned a homework problem, right? And so this qualitative approach is super useful, especially that quiz that he did. Let me just back up to that quiz. This type of quiz is really, really great to help students. Okay, now I'm starting to understand what I'm looking for. It turns out in the lab, these are actually really hard to see. So if you say, oh, we'll go in the lab and count how many sub-maximums there are to figure out how many slits we went through, I find that to be hard. I don't know how other people deal with that. And another way to think about it is how narrow the main bright spot appears and frankly how bright it is. But yeah, this qualitative approach to this stuff is really great. And I'm not 100% sure whether this was like, hey, we're going to hit this section 36.3 in class. I just wanted to give you a heads up, or if this was sort of this was the amount of sort of support they're going to get. It's not clear to me, but I could see it working either way. All right, awesome. Well, hey, everybody, have a great day. And remember, physics teachers are awesome.